What the heck is a Markov Chain Monte Carlo model? Let's tackle that question together right now. Hi, I'm Oliver, PhD candidate at UC Berkeley and private tutor, and welcome to my Intro to MCMC series. Primarily, this is based on UC Berkeley's Data 140 course, but it's suitable for anyone getting into Markov Chain. Today, we are going to use MCMC in plain English with an SIR model from epidemiology. Let's get started. Here's our plan for the day. We're going to answer questions: what is a Markov chain, what is Monte Carlo, and how MCMC helps when math is messy. We're going to answer this all with a real-life example using an SIR model to model the spread of the chickenpox virus in an elementary school. So what is SIR? So let's say we have this population of 100 students in the school. They all start out as healthy, which means susceptible. Each week, each has a 0.25 probability becoming infected with the chickenpox virus. Now, that also means each individual has a 0.75 probability of remaining susceptible. For the infected children, the children that currently have chickenpox virus, each has a 50% chance of staying infected into the next time step, and they also have a 50% chance of going from infected to recovering, the R in SIR. So we're saying in purple, there's a 0.25 or 25% chance for each individual in S that they will move into I on each time step. Then the arrow back on itself is when someone starts in S and they end in S, or start as I, end in I. Same thing with R. So we would actually make another one here. So it just means that they're gonna remain in their state on the next time step. This kind of model uses something called discrete time. There is a change of all individuals, so T of 1, T of 2, T of 3, T of 4. We'll see more about that below. Now, the issue with something like this is that the math for this probability model is very ugly. There's no neat way to integrate or normalize to get exact probabilities. This is exactly where Markov chains come from. So Markov chains are a way to hop between states with certain probabilities at each discrete time step. The next state depends only on where you are now. So if that's Markov chain, what is Monte Carlo? So Monte Carlo means randomness to estimate state values. For example, let's say you roll a die 100 times and you get the average of those rolls to approximate the mean. That is an example of Monte Carlo. Finding these. With Markov chain, you need to use discrete time step, some number of states, so some finite number of states. There's connection between the states, that's known as connectivity, and the population is spread across all states of the model. For each time step, individuals from one state move into another state based on probabilities called transition rates. So let's look at some of those examples. So our time step for this model is going to be 1 week. 1 week time steps means that the model is all at week 1 at first, and then all the values update at the same time to week 2. Model values update from week 2 to week 3, all at the same time, so forth. So it's discrete time steps. With each time step, i.e. each 1 week to the next, there's a 0.75 probability of that. In other words, 75% chance for each individual that's susceptible to remain insusceptible. Similarly, there's a 25% chance that each individual unsusceptible will become infected. There's a 50% chance that each infected individual will stay infected. And then there's another 50% chance that each infected individual will recover. In order to actually complete this, we would have to write one more. Let's say that we're going to go from recovered to recovered. What do you think the probability is going to be for going from R back into R? People only ever get sick with the chickenpox virus, at least as kids, one time. So it's one and done. After someone has gone through the state of I, being infected, once they recover, they stay that way. That's a little bit of an assumption of our model, 1.0. So the way we represent these numbers are with something that's called a state change matrix. So it's also called a transition matrix, but it looks like this. The way that you read these is you look from the index of your row. Remember, rows go across the screen, columns go down the screen. So you look on your index from row to column. So in other words, this 0.75 in the top left is saying if we start at state 1, which is S, what is the probability of each individual moving into state 1, is column 1, which is S. So it's the 75% chance that individuals that are healthy remain healthy into the next time step. Compare that to 0.25 here that I made bigger in purple. It's a 25% chance that each individual that's in state row 1 then end up in state column 2. So from state 1 to 2, i.e. S to I, 25% chance. And we can see that this means there's no chance that someone that is susceptible will ever go directly to recovered. Again, we're using a simple model. We're not implementing vaccines. So for our purposes, that's 0. Now, the same thing holds true with the other ones. So read as transitions from row to column index. For example, going from state 1 to state 2, and 2.5, like I said. So now let's tie all this together and bring it back to the SIR model. Let's work with it. The formula for this to get the unnormalized posterior is as follows. So you get the score state calculated from the likelihood of data given state times our prior assumptions about state. So what does that actually mean? Let's see it in action. Remember, we're saying we have 100 healthy kids, which means susceptible, that are starting. Somehow there's going to be exposure to the chickenpox virus, and we start seeing exposure in the first week. We can either do column-wise representation of this equation, or we can do row-wise representation. We're going to end up sticking with column-wise, but I just want to show that you may have a teacher, professor, TA, GSI that's showing you this in either way or both ways, and both are correct. They're equal to each other. So our transition matrix, I'm going to call it TM down below, is exactly our probability matrix that we've talked about, our state change matrix. So for column-wise, we're going to have this row of individual state values, and that gets multiplied column-wise of the transition matrix. So what that means is the first value here, the 100, that gets multiplied by the first value in the first column, plus the I value gets multiplied by the second value in the first column, and same with the R. All of that gets added together to come up with the number of individuals in state S after T plus 1. Same thing, but moving on the same exact row, but you multiply it by the second column to get the second number I. Same thing with the last one, the last value to the third column to get the number of individuals that are recovered at T plus 1. Row-wise looks similar, except we take our transition matrix first. We have to transpose it, so doing like a mirror flip, and then that gets multiplied to this vertical vector, which represents healthy kids on top, infected, second state, recovered, third state, bar. We start with T of 0, and let's do T plus 1, so one time step. We're going to use column-wise representation, like I said. So in order to calculate what S is going to be at T plus 1, this is what it would look like. We have our row representation of the individuals in each state, 100, 0, 0, multiplied by the first column of the transition matrix. So row by column. Now, it's worth pointing out that when you do column-wise representation, column-wise means you're using a column of the transition matrix. Because if you notice with column-wise representation, the number of individuals in each state is represented as a row. So a little confusing. Column-wise actually starts with a row. Anyway, I color-coded these so they go together the way I said, and that gives you 75. There will be 75 individuals in state S at T plus 1. Let's see that for everything now. Again, we have our row of values multiplied by whole transition matrix. We wind up with 75, 25, and 0, visualized here with the model form, at T plus 1. So 75 healthy kids the next week, 25 that are infected with chickenpox, and 0 that have recovered so far. So next time step, we just do the same thing, except we update the first values, just the number of individuals in each state. So 75, 25, 0. You can see that at each time step, you start with whatever value was returned from the previous time step. So the updated values from one time step become the initial values in the next time step. So we end up with 56 susceptible, 31 infected, and 13 have recovered. Going to another week, so what is this going to be? Start with 56 susceptible, 31 infected, 13 recovered, multiplied by our transition matrix. What do we wind up with? You do the calculation yourself, you should get something like this, starting the initial week, T0, into the first week. So 1 week, 1 to 2, 2 to 3. So we've gone 3 weeks. We've gone from 100 healthy kids, 0 infected, 0 recovered, to now 42 healthy, 29 infected, and 29 recovered. So what did we learn today? 1, we learned what MCMC is and why we would use it. We learned that MCMC can help you take I can score this problems into I can sample and estimate problems. 3, we created a real time-based disease spread model for the chickenpox virus. Comment MCMC 2025 below for today's slides and more examples of Markov Chain Monte Carlo models. Next time, we're going to cover the Metropolis algorithm and walk through solution of UC Berkeley's Data 140's sausage chain problem. Thanks for watching, guys.